Good morning, ladies and gentlemen, Mr. Chairman. We did a an investigation, a small, rather general investigation, and we were interested in the question: how does selection affect the conditions in a validation sample? So we focused on the property of reliabilities as measures of the precision of estimates, and the question was, how much will a future more reliable estimate deviate from the current one? Our calculations were based on model-derived reliabilities and related multivariate normal distributions of true breeding values and blobs, and had this general form. So we modeled a true breeding value, a PA, and GEBV, and a daughter-based conventional EBV, and we assumed the covariance structure given here for the breeding values. This structure is quite similar to the proposal by Paul van Reyden that he gave for the blending of genomic breeding values. Given that this structure is the true distribution, we can model the effects of selection by calculating explicitly the conditional means and covariances. So we used the general formula for conditional means, and this expression shown down there that is given by Henderson to calculate the effects of selection on the covariance structure. So if you have calculated the covariance after the selection effect, like it's given down there, then you can calculate all kinds of expectations from this covariance structure. So for example, you can calculate expectations for correlations, for regressions, or for any kind of linear combinations of the breeding values. For multi-step scenarios, we used simulation because after the first step of selection, the assumption of multivariate normality does no longer hold. So let me illustrate to you the general aspects. Assume you have this validation group where you have an EBV with a squared correlation or reliability of 0.65, and you make a scatter plot against the true breeding value. Then you have simulated a squared correlation of 0.65, and you would re-estimate a squared correlation of 0.65 from these data points. And if you have a look at the prediction error distribution, you would observe a standard deviation of 7.1, and if you assume your re-estimated squared correlation of 0.65 to be right, you would also expect a standard deviation of 7.1, so everything is as you would expect here. So let me now introduce selection to the picture. So now you have selected your validation sample on a correlated parent average with a reliability of 0.38, and you have chosen the better 25%. Then now you would re-estimate a squared correlation of 0.51. And however, and quite obviously, the prediction error distribution has not changed accordingly, so you would still observe 7.1 as a prediction error standard deviation. However, if you would assume the 0.51 to be the real reliability in the sample, you would expect a standard deviation of 8.42, and that is an underestimation of the true precision of your estimate. Now, you cannot observe the true breeding value in real life, so you can take a proxy, and the proxy throughout the rest of the talk is meant if you use a GEBV and plot it or compare it to a conventional daughter-based EBV with a reliability of 0.89. In this case, you have simulated a squared correlation of 0.63. However, because of the selection on correlated PA that you have applied, you would re-estimate only 0.46 in this case. And observed standard deviation would be 6.95. However, if you assume 0.46 to be the true reliability from cross-validation or forward prediction, you would expect a standard deviation of 8.88. And so, again, you underestimate considerably the true precision of your estimate. So let me now show you some results for 3 scenarios we did. The one is the selection on PA, where the proportion selected was 25%. One is the selection on EBV, representing selective genotyping effects, with a proportion selected of 75%. And one is a combination of both. And shown here are only the values for the proxy, meaning the relationship between the daughter-based conventional EBV and the GBV. So let's now have a look at the squared correlation. Simulated was 0.63, a squared correlation. With selection on PA, this reduces to 0.45. And also with selection on EBV, with selective genotyping, this drops down considerably to 0.47. And in the combination of both, there's an additional effect, and you even get out lower. Let's have a look on the prediction error standard deviation proxy. The proxy is what we would observe in this case, and the prediction error standard deviation CV is what we would expect from the squared correlation from our cross-validation. And as you can see, we get an increasingly conservative assumption about the true precision of our estimates, and we would increasingly underestimate the true precision in the sample. Another point that is worth to be mentioned is that this PESD proxy, which is the distribution of the differences between the GBV and the EBV, is quite stable and is not very much affected by the effects of selection on the sample. Let's have a view on means. Here, if we have selection on PA, we can see that this has an effect on the means, but all means are changed accordingly. This is not true if you have selection on EBV, like in selective genotyping. Here you have the highest value, you have an unbiased EBV. You would see an unbiased EBV. However, you would see that the GBV and the PA average is lower, and maybe you would have thought that this is an effect, that these values are biased. However, this is only an effect of the pre-selection or the selection on the EBV that you have done in your sample. And the same is true if you combine the both selection steps. Last table is on intercepts and slopes for the regression. Again, let's have a look first of all on the regression on the expected B1. If you regress the true breeding value to the GBV, with selection on PA, you wouldn't have no effect on your expectation. It would still be 1. However, if you have selective genotyping, and that is what I think is quite clear, then you have an effect on your expectation, and it drops down to 0.8. Interestingly is that if you have a combined selection on PA and EBV, you have an additional effect on the expectation, so the expectation drops down a little bit more. And again, let's have a look at the proxy where we regress the conventional daughter-based EBV on the GEBV. Then we start even in the unselected case with an expectation that is well below 1, and this expectation drops down with selection accordingly. So the general conclusions would be that squared correlations derived from cross-validation can be heavily influenced by effects of selection on the validation sample, and it should be pointed out this can mean that you have selected animals in your cross-validation or in your validation samples. It could also be that you have unintentionally made some data selection, so you only have looked at the best animals, at the most reliable animals, and this can have an effect like selecting. These effects of selection in real life might be hard to characterize, both in scope and nature, and therefore conclusions from cross-validation correlations about true precision and bias of estimates might be limited. The distribution of differences, this prediction error standard deviation proxy, this difference between GEBV and conventional daughter-based EBV, is a relatively robust measure, and it's not strongly affected by selection effects. And in my opinion, or in our opinion, it could be a helpful extension to the GEBV test. This approach is capable for calculation of expected B1 under selection. However, it should be clear that if we use expectations for the regression of true breeding value on GEBV, we don't have true breeding values, and everything depends then on the deregression step to give our EBVs the distributional properties of the true breeding value. So everything is left to the deregression. Instead, we could use the B1 from the regression of EBV on GEBV, and that would allow us to test simultaneously for the coherence of the estimates and the assigned reliabilities. So you might argue that selective genotyping is not a big problem in the future, but there's another problem coming up, and which is mentioned by the talk before, that in the future we will have validation samples that were entirely pre-selected on GEBV. Here's given an example where we selected 10% on a reliability of 0.65, and this selection will have huge effects on our expectations, and I think it's time to think of adjustments that we can make to get the right expectations for our GEBV tests. Thank you for your attention.